All right, I'm going to redo that because I wasn't recording. Sorry. Okay. Sorry, I did this already and I wasn't recording. We have intermolecular forces is the first topic we're going to go through. If you remember back to your unit for electronegativity and those values and how they will determine the intermolecular forces. Now, we're not talking about the forces that hold a molecule together. It's talking about the forces that hold two molecules in a liquid together. So, intermolecular forces determine the boiling point, the melting point, volatility, so on and so forth. Okay, let's look at electronegativity. So let's say we've got two atoms and they bond together using their outer shell. Let's use carbon and hydrogen as an example. Hydrogen has an electronegativity value of 2.2. Anyone want to find me the electronegativity value of carbon? No? Okay. So 2.55. So we know that carbon and hydrogen will evenly share the valence electrons. Evenly share the valence electron. And we know this because the electronegativity value is less than 0.5. The difference between these two is less than 0.5. So why is it called non-polar? Because the electrons are shared evenly. So there's 8 valence electrons, 4 around here. I mean, I know in carbon hydrogen it's not this, but let's just pretend it is. And the term pole coming from a magnet. So there is no uneven poles here. The charge or the electrons is distributed around the two atoms evenly. So anything that has this kind of bonding, so if we had CH4, we are looking at very weak dispersion forces. So if we look at carbon and hydrogen, at some point in this molecule, even though they're shared and distributed relatively evenly, there will be more on this side than there will be on that side. It's very weak. So dispersion forces, very weak. So if we were looking at CH4 or methane, it has a boiling point of minus 189 degrees. So dispersion forces, minus 189 degrees. Okay, everybody understand that? It's non-polar because the electrons are shared evenly. So the intermolecular forces or the dispersion forces are really weak because there's no positive or negative charge really, not for any extended period of time. Okay, let's look at polar. Okay. So polar bonding someone just asked if this session was on. Sorry, I'm just going to pause recording for a second. Okay, so polar bonding is caused by electronegativity value difference of greater than 0.5. So the classic one, and I'll always use organic chemistry as an example, is carbon and oxygen. So again, if someone wants to have a look, at the electronegativity value of oxygen, so oxygen is 3.44. So you can see there, the electronegativity value is 0.1. What does this mean? I hear you asking. We have carbon and oxygen here. And that's what a molecule is supposed to look like. So we pretend that's what a molecule is supposed to look like. Hi Ross, sorry about that. Because oxygen has a greater electronegativity value than carbon, what it does is it hogs the electrons. So oxygen already has a non-bound pair of electrons. It's in group 6. And when it binds with carbon, it steals 4 electrons. It only needs 2. Because it's in group 6, it only needs to gain 2 electrons. So it has 2 non-bonding pairs that aren't involved in this covalent bond with carbon. And then it'll hog all of the electrons. 3, 4, 5, 6, 7, 8. Let's say it hogs 6 and the other 2 are here. If I've got all of the electrons stacked on the right-hand side of oxygen, oxygen is going to have a significant negative charge. Carbon is going to have a more positive charge because all the protons in its nucleus are no longer shielded by the electrons. So let's say another carbon to oxygen molecules comes along. Oh, look. Oxygen is negatively charged. Carbon is positively charged. We know that if we stick a positive end of a magnet together with a negative end, we will get bonding. Now, the reason it's stronger is because it's more permanent. The difference is bigger. Eventually, these electrons will come around and break this bond. So if we have CH4 minus 189 degrees Celsius boiling point, a molecule with carbon and oxygen that's the same size will have a boiling point of about minus 90 degrees Celsius, or minus 89. So polar bonding, big electronegativity value difference, uneven sharing of the electrons, because carbon donates 4, but oxygen only needs 2, so it's green. So oxygen, really negatively charged. Carbon, the protons in its nucleus are no longer shielded by the electrons. They come up next to the oxygen, which is completely surrounded in electrons, and you get electrostatic attraction. In organic chemistry, this is called dipole forces. Okay. Now we get to the real, everything else is a white bond. Okay. Hydrogen bonding. So, hydrogen bonds. So, as it suggests, it has hydrogen. Shock, I know. Bound to oxygen, nitrogen, or fluorine. We know hydrogen's electronegativity value is 2.2. Fluorine, the most reactive element, they make Teflon out of fluorine because it will not react with anything else once it's tightly bound to something. So again, if you're watching this, or if you sat there, Google the electronegativity values of oxygen, nitrogen, and fluorine, and I'm just going to grab a drink. So, talking all day. Oh, that's so Izzy says oxygen is 3.44. What's nitrogen? Should be 3.0. 3.04, same thing. Okay. So you can see that there is significant electronegativity difference. The other, so with oxygen, you end up with 2 unbound electrons. Nitrogen, you end up with 3. Fluorine, you end up with 1. So if we have hydrogen and oxygen, and I'm going to attempt to draw the structure of water, probably unsuccessfully. So let's look at water. All of the properties of water do not make sense. Let me shut this door. Do not make sense. If water was ever so slightly different, it wouldn't be. It'd have a boiling point. It should have a boiling point of 34 degrees. But it has a boiling point of 100 degrees. Why is that? Because of hydrogen bonds. So this is the structure of water. These electrons from hydrogen go on to oxygen. Hydrogen becomes positively charged. Oxygen is so electronegative that it permanently steals the electrons. So hydrogen becomes negatively charged, positively charged, and the oxygen becomes super negatively charged. So another water molecule lines up. We know that so we get bond between we get another water molecule. We start building this diamond shape. So this is hydrogen bonding. When hydrogen is bound to oxygen, nitrogen, or fluorine, and you just keep building this lattice, and it becomes a diamond shape. So hydrogen bonds are the strongest of the intermolecular forces. They occur when oxygen is bound to nitrogen, oxygen, nitrogen, or fluorine are bound to hydrogen. Shock horror, I know. So water has a boiling point of 100 degrees when it really should only have a boiling point of, I think it's 37 degrees, but it's because of this hydrogen bonding that allows it to have the higher boiling point. So to, I guess, summarize, we have non-polar or dispersion forces, which are the weakest. We then have polar bonds, which are the second strongest. We then have hydrogen, which are still technically polar bonds. But they are the strongest. All right, take 30 seconds. And it's all to do with electronegativity. The higher the difference, the higher the polarity, stronger the bond. All right, everyone take 30 seconds to write that down, and then we will look at VSEPR. Okay. So VSEPR. Anybody heard of it? Anyone know what it is? Anybody suffered through doing it? Valence shell electron pair repulsion theory. Very, very boring. But we have to do it. So we know that electrons are negatively charged. They repel each other. When you have electron pairs involved in bonding, they will arrange themselves dependent on the number of bonds. If there are two pairs, they will arrange themselves in a linear fashion. So what's an example of linear? Why can't I think of one? Something sat inside for the past. So O2. O2 is probably not the best. Probably not the best example. Why can't I think of one? There we go, CO2. So there's two atoms involved, or two pairs of electrons. How do I know that? Don't ask. Two pairs. So we would have carbon. So when we have a linear molecule, the electron pairs, which are these, are at a 180-degree angle to each other. So if there's two pairs, bonding pairs of electrons, they're at a 180-degree angle because they're physically as far away from each other as they possibly could be. We then have a shape called trigonal plane. Shocker, this is 3 bonding pairs. So if we use an example, so got boron chloride. So we stick boron in the middle. When you're doing this, if you haven't done any Lewis dot structures, and I think we might go through those later. Oh yeah, we do a little bit. The least electronegative atom goes in the middle. Does anyone want to tell me what group boron is in? No one? So it's in group 3. Okay. So if there are 4 bonding pairs, in CH4 or methane, it takes up the shape tetrahedral. Carbon is in group 4, so it has 4 bonding pairs. To go with the trigonal planar, sorry, before I they are at 120 degrees away from each other. And that's when there's 3 bonding pairs. Okay, so CH4, I know I said the least electronegative goes in the middle, but with CH4, here's a hint. You can tell what shape it's going to be by the group number of the first element and how many of these hydrogens there are. Carbon, shock horror, is in group 4, so it will have 4 bonding pairs. They are arranged at 90 degrees to each other. So you can see with each shape, they're still trying to stay as far away from each other as possible. They don't like each other. They think the other one has cuties. This is not the most exciting topic. I will deal with that. So if we have 5 bonding pairs, bonding pairs, we get this weird shape called a trigonal bipyramid. So if we have, so let's go with phosphorus tetrafluoride. How do I know it has 5 bonding pairs? Because it's 5 fluorine, and phosphorus should be group 5, otherwise I made a big mistake here. So PF5. So we have phosphorus in the middle. Yeah, just arrange our fluorine out like this. Oh no, they're all 90 degrees. Where does our 5th fluorine go? Oh my gosh. It like kind of kicks up at the side here. This little sign means it's coming forward off the molecule. So all of these electron pairs are still 90 degrees away from each other. That means this different shape here means it's on a different plane. So that is called a trigonal bipyramid. We'll use it to determine, this method to determine the shape of a compound. Right, we have one more. It makes a strange shape. And that shape is octahedral. So if we have something in group 6, like sulfur, we have S, F, 6. How do I know it's got 6 bonding pairs? Because there's 6 fluorines attached to one sulfur. Not just a pretty face. So we have sulfur in the middle, and our usual 4 fluorines around the side. Okay. So how do we sort this out? We do our, so that's coming out to the front. And the other one kicks out behind the S. So this has 6 bonding pairs. All right, let me go through that again with just my tutor. Generally speaking, for a linear molecule, there's 2 pairs. So usually means something in group 2. If we have trigonal planar, three pairs. The first element will be likely from group 3. If we have tetrahedral, I think you can see where this is going. 4 pairs. Imagine my shock. First element will likely be from group 4. we have the trigonal bipyramid. Five pairs. Shakara. I think phosphorus is in group 5. Could be made to look very silly here. It's in group 5, what group 15? I'm smart. I've been saying so in front of the computer for too long. So if we then have our final shape, anybody remember what it was? Octahedral. A lot of people get confused and think it has 8, which I mean, I can see why. It has 6 bonding pairs. Usually be in group 6, notable exception, SF6. Shakara, sulfur is in group 6. So instead of trying to learn everything, use my hacks and tips and tricks to help you make your life in chemistry easier. Certainly don't know everything there is to know about chemistry, but I certainly know how to learn it efficiently. So that's VSEPR. The take homes here are that because the electron pairs are all negatively charged, they will arrange themselves that limits their repulsion. If there's too much repulsion, they will have too much instability. I will see everybody next week. I'll see some of you later on in the week. What do we have next week? We've got, oh, we've got chromatography and gases. How fun. I will see you guys next week. Look at my new messy office, still not finished yet. Have a fantastic week.